Hello, my name is Kang from Hwan University, Korea, or SKKU for short. Today I am excited to present my latest research on low-rank compression for IMC arrays, or in-memory computing arrays. This work will be presented at session TS21 on Wednesday, 11:35 a.m. I hope to see you all there. In this presentation, we will examine the challenges of applying low-rank compression to IMC architectures, particularly the issues of accuracy drop and array utilization. We will demonstrate how these challenges can be effectively addressed by redesigning both the low-rank decomposition and mapping algorithms, leading to significant improvements in throughput and accuracy, and all without requiring additional hardware support. Now let me begin by introducing in-memory computing architectures, or IMC. As many of you are aware, one of the biggest challenges in deep learning hardware is not computation, it's memory. IMC architectures address this issue by unifying computation and data storage, enabling computations to be performed directly within the memory. This eliminates the need for the data movement and all the associated latency and energy overhead. Analog IMC architectures leverage non-volatile memory crossbars, such as ReRAM-based arrays, to efficiently execute matrix vector multiplications. As shown in the figure on the right, the input of the neural network is fed into the IMC array as voltages. Subsequently, a current flows through the MEM registers following the Ohm's law, thereby performing multiplication operations. The resulting currents are accumulated along the columns, obeying the Kirchhoff's law, which naturally performs the addition operations. This process allows IMC arrays to execute MVM operations with a high degree of parallelism. By leveraging the energy efficiency and parallelism of the analog IMC arrays, we can significantly accelerate deep neural network computations. Of course, DNN computation in IMC arrays can be further accelerated by adopting latest model compression technique, such as pruning. However, sparsity generated by these pruning techniques often do not lead to hardware performance boost and requires specialized hardware support. Here are some examples for IMC arrays. Now, one way to support pruning is by zero skipping or power gating. We basically zero out an entire row of the weight matrix, skipping the computation of that row. To achieve this, we need some sort of a peripheral to enable zero skipping, such as power gating hardware. Although this may help with energy saving, it will not lead to cycle or crossbar area reduction. To overcome such limitations, another way is to compress the mapping itself to form a smaller weight matrix. However, this will require a use of a multiplexer to route the input to the correct rows of the IMC array. And multiplexers are expensive, both in terms of area and energy. This also complicates the overall data flow, making the design less efficient. To summarize, adopting pruning for IMC arrays suffers from these two drawbacks. One, it requires additional hardware peripherals, as we have seen before. Two, we must use structured pruning as we need to skip the entire row. Otherwise, we cannot compress the weight matrix due to its parallelism. Motivated by these challenges, we explore the use of low-rank factorizations to compress the weight. Low-rank compression simply factorizes our weight matrix W into two smaller matrices, L and W, as you can see in the figure above. Another way to look at this is the ijth element of the weight matrix, Wij, is given by the dot product of Li, vector of matrix L, and Rj, vector of matrix R. We can interpret this as that the vector Li is encoding the information of ith row of the weight matrix, and Rj, jth column of the weight matrix. Now, the great thing about the low-rank decomposition is that the decompression process only requires matrix vector multiplication operations, and we know that IMC is really good at this operation. This also means that no additional hardware support is needed, like pruning. However, Adopting low-rank compression comes with its own set of challenges, namely accuracy drop and array underutilization. Firstly, we see significant accuracy drop with low-rank compression compared to other compression techniques. We attribute this shortcoming to the information bottleneck in the L matrix. As we mentioned previously, the vector Li encodes ith row and Rj jth column. Note that the length of the vectors Li and Rj is the same. However, Li is compressing way more elements of W. Thereby, it bottlenecks the compression quality, leading to a significant accuracy drop. Secondly, low-rank compression causes array underutilization. Because we factorize the weight matrix into two smaller matrices, the dimensions of the smaller matrices may cause idle columns and idle rows, thereby causing array underutilization and lowering the overall throughput. To summarize, low-rank compression on IMC arrays adopted as is will yield 1. Lower accuracy, and 2. Lower utilization, and therefore lower throughput. To address these challenges of low-rank compression, we propose two novel techniques. The first technique is the group low-rank compression to address the accuracy drop issue. The key idea here is to partition the weight matrix W into multiple groups and then apply low-rank compression. The second technique is SDK mapping for low-rank compression. The key idea is to use the SDK to utilize idle columns for processing multiple sliding windows in parallel. And we'll see later what SDK mapping exactly is and how it works. Let's start with group low-rank compression. By partitioning the weight matrix into multiple groups and then applying the low-rank compression, we are basically introducing additional Li matrix. In other words, we have more Li vector to encode the elements in W, thereby alleviating the previously mentioned information bottleneck. We also find that the reconstruction error of group low-rank compression is upper bounded by that of the traditional low-rank compression for an arbitrary number of groups, and this is shown in Theorem 1. Intuitively thinking, you can convince yourself that this is true as you are introducing more parameters. For the detailed proof, please see our paper. As a side effect, group low-rank compression also results in improved row utilization in the second multiplication. Note that the output from the second multiplication, each with the matrix L1 and L2, needs to be summed anyways. Therefore, the two L matrices can be stored in the same IMC array, making a better use of idle rows that were previously presented in the second multiplication stage. To summarize, with the proposed group low-rank compression, we first achieve better reconstruction error, which hopefully will translate to accuracy improvement. And secondly, we partially address the underutilization issue by improving the row utilization in the second multiplication stage. Now let's move on to the second technique, shift and duplicate kernel mapping for low-rank compression, or SDK mapping for low-rank compression. But wait, what is SDK mapping? SDK is a mapping technique which improves throughput by utilizing idle columns to process additional sliding windows. As shown in the figure on the right, image to column or IM to call mapping processes a single 3x3 sliding window, and this often results in low column utilization, especially if the number of output channel is few. SDK addresses such issue by processing a larger sliding window, in this case 4x4. It achieves this by appropriately shifting the kernel and duplicating them in the idle columns, effectively processing 4 3x3 sliding windows in parallel. However, the problem here is that SDK was designed for convolutional layers, not low-rank decomposed layers. And the challenge is to transplant this technique to our low-rank setting. As shown in Theorem 2, we propose a formulation of SDK for a low-rank decomposed matrix. More specifically, we found that low-rank decomposition of SDK mapped weight matrix is given by the multiple of diagonal block matrix of L an SDK mapped R matrix. By doing so, we can improve the column utilization of the first multiplication stage as shown in the figure on the left. For the detailed proof of our theorem, please check our paper. In summary, with our two proposed techniques, we can achieve better reconstruction error and also improve row and column utilization. Move on to the experimental results. Here's our setup. For comparison, we employ pattern pruning baselines, which can be easily adopted to IMC array for computational speedup. For evaluation models and datasets, we employ ResNet20 paired with Cypher10 and wide ResNet 16-4 paired with Cypher 100. We choose these two combinations as they are most frequently evaluated on various IMC compression papers and also in our baselines. For model training, we trained all of our models, both pruned and low-rank compressed, using a quantization-aware training approach with Dorfa quantizer. Weight and activation precisions were set to 4-bit. For hardware evaluations, we built a simulation tool based on NeurSim and ConvMapSim simulators to measure the energy consumption of the different compressed models. Here, we first compare our method with pattern pruning baselines. We plot the Pareto curve of different compressed models, where y-axis shows the accuracy and the x-axis shows the computing cycles. And we repeat this for different deep learning models and IMC array dimensions. We vary the computing cycles of our method by choosing different combinations of rank and group parameters, versus for pattern pruning approaches, we vary the number of entries for the patterns from 1 to 8. As you can see from the graph, the proposed low-rank compression method achieves similar performance or better. In the case of ResNet20, our accuracy decays at a slower rate, achieving slightly better accuracy than the pruning approaches. In the case of wide ResNet 16-4, our method achieves significantly better performance, achieving up to 2.5 times speedup or 20.9 percentage point accuracy improvement. The performance improvement in ResNet20 is less noticeable than in wide ResNet 16-4 because ResNet20 simply has too many idle columns. Although the proposed SDK mapping will offset this underutilization, it can only do so much. Next, we picked a compressed model with smallest computing cycles and accuracy drop of less than 1% and evaluated its hardware performance, namely energy consumption. As you can see from the bar chart, we achieved up to 62% point reduction in energy consumption with ResNet20 and up to 71% reduction with wide ResNet 16-4. We also compared our work with other compression methods besides pruning. First, we compare our work with quantization techniques. Here, we vary the weight bit width of the quantization baseline from 1-bit to 4-bit, while the activation bit width is fixed to 4-bit. Our method is quantized to 4-bit of weights and 4 bits of activation, as mentioned previously. Here, we can see that we achieve speedup of 1.5 times and 1.8 times on different IMC array dimensions. We also compare our method against the traditional low-rank compression, that is, without the proposed group low-rank compression technique and SDK mapping. From the graph, it is clear that the traditional low-rank compression on its own fails to achieve significant improvement in terms of both accuracy and computing cycles. The proposed method achieves around 1.5 times speedup compared to the traditional low-rank compression. In conclusion, in this work, we tackled the problem of adopting low-rank compression on IMC arrays. We were met with two challenges. First was the accuracy drop, and the second was the underutilization. We addressed these two issues with two novel techniques, group low-rank compression and SDK mapping. Our evaluations demonstrate that the proposed technique can achieve up to 2.5 times speedup, 20.9 percentage point improvement in accuracy, and 71% reduction in energy consumption. These results highlight the potential of low-rank compression technique, especially noting that it does not require any additional hardware support like pruning. For future work, we hope to explore efficient optimization of rank and group parameters and also design a post-training method to perform the proposed method. Thank you, and feel free to reach out if you have any questions or comments.